Hello grade 12 and welcome to this video on the principle of conservation of linear momentum. Now, in order to completely understand the principle of conservation of linear momentum, it's important that you understand what is meant by the term isolated system. So in physics, we say that an isolated system is a system on which the net external force is zero. So this can sound very confusing because we know that we normally make use of the principle of conservation of linear momentum when we have two objects that are colliding or exploding apart. So that means that there must be forces, and yes, grade 12s, there are forces that are going to be acting in the system, but the net external forces need to be zero. So we say an isolated system excludes external forces. These are forces that originate outside of the colliding bodies. So for example, friction is considered to be an external force. And therefore, when we are considering the principle of conservation of linear momentum, we would like forces like friction to be zero. The only internal forces that we're interested in are the contact forces between the colliding objects. This is when we are dealing with the principle of conservation of linear momentum. So there are forces, but the net external force should be zero. Now, the principle of conservation of linear momentum says that the total linear momentum of an isolated system remains constant, or you can say it is conserved. This is a very important definition or principle, so please ensure that you learn it off by heart. In symbol form, we have that the sum of the initial momentum of the two objects, of course, is equal to the sum of the final momentum of each object. So let's say that we are considering a collision between two objects that are separate in the beginning and after the collision are separate again. Then we would say that the initial momentum of object 1 plus the initial momentum of object 2 is equal to the final momentum of object 1 plus the final momentum of object 2. We can expand this so that we have this on the left hand side and that on the right hand side. Now sometimes instead of having the objects separate in the beginning and at the end, you may deal with an explosion, for example, a bullet in a rifle. In that case, we start off with two bodies that are in a sense joined together, right? So the bullet will be inside of the rifle. That means that in the beginning they have exactly the same velocity. So we can write the left-hand side of the equation as you can see displayed to your screen. And since after the rifle is shot, the bullet and the rifle are separate, you'll see that on the right-hand side the formula is exactly the same. In other cases, we may have that there are two bodies that are initially separate, but then they bump into each other and then move together as a system. In that case, we say the initial momentum of object 1 plus the initial momentum of object 2 is equal to, we add together their masses, and since they are moving as a system, their final velocities are exactly the same. So the main version of the formula is this one right at the top, but you may need to use the other two at the bottom. Please remember, grade 12s, that the formula for momentum is mass multiplied by velocity. I very often find that learners, instead of saying mass multiplied by velocity, say mass multiplied by velocity squared, or they go and put a half in front of this formula because they confuse momentum and kinetic energy. Please be very careful and always remember to consult your formula sheet if you get confused. Let's now take a look at a few problems involving the formulae that we spoke of or that I showed you above, as well as the principle of conservation of linear momentum. This question says ball P of mass 0,16 kilograms moving east at a speed of 10 meters per second collides head-on with another ball Q of mass 0,2 kilograms moving west at a speed of 15 meters per second. After the collision, ball P moves west at a speed of 5 meters per second as shown in the diagram below. Ignore the effect of friction and the rotational effect of the ball. So we are being told to ignore the effect of friction because friction, remember, is an external force. And in order for us to apply the law or the principle of conservation of linear momentum, all external forces need to be ignored or should be zero, as in this case. So question number 4.1 says, define the term momentum in words. I'm going to leave that up to you and move on to the second question, which says, calculate the velocity of ball Q after the collision. So in this case, we're going to be making use of the ordinary form of the principle of conservation of linear momentum as follows. We say the sum of the initial momentum is equal to the sum of the final momentum, and we expand the formula. So very important, we remember that momentum is a vector quantity. So direction is very important. They've provided us with two directions, east and west. How about we choose east as positive? This means that west is going to be negative. We need to sub our values into the formula. The mass of the first object is 0.16 kilograms, and this object starts off with an initial velocity of 10 meters per second eastwards. So we plug in 10. We then say plus the mass of the second object. The mass of the second object was given to us as 0.2 kilograms. So we plug in 0.2 kilograms and its initial velocity is negative 15 because it was initially moving towards the west. The mass of the first object is still 0.16, and we were told that after the collision it moves towards the west at a speed or a velocity of 5 meters per second. We add to this 0.2, and we do not know the final speed of this object, which is object Q. If you would like to, instead of labeling them M1, V1, M2, V2, you can make use of P and Q instead, and that will also suffice. When we plug this into our calculators, we find that the final velocity is going to be equal to negative 3. Of course, this is the final velocity of ball Q, so I'm going to turn to Q now, and this is going to be 3 meters per second. We need to give our answer direction. The direction here will be towards the west. Since east is positive, west is the direction that is negative. The marks will probably be awarded as follows. You'll get 1 mark for your formula. You get 1 mark for what you substitute on the left, 1 mark for what you substitute on the right, 1 mark for your magnitude with the correct SI unit, and 1 mark for the direction that is included. That gives you a total of 5 marks for this question. Let's now look at an example involving an explosion. This question says a bullet of mass 20 grams is fired from a stationary rifle of mass 3 kilograms. Assume that the bullet moves horizontally. Immediately after firing, the rifle recoils. This means the rifle moves back with a velocity of 1.4 meters per second. Calculate the speed at which the bullet leaves the rifle. So we are dealing with two objects here, a bullet and a rifle. We're dealing with two directions. It is forwards and backwards. We see we're given the mass of the bullet as 20 grams. We need to convert this to kilograms. It's the same as 0.02 kilograms because to go from grams to kilograms, we divide by 1,000. The mass of the rifle is given as 3 kilograms. The rifle's final velocity is 1.4. We are looking for the bullet's final velocity, and we see that they both start off at a velocity of 0 meters per second. Now, when you go and you label, you're welcome to use a B for bullet and an R for rifle instead. I'm sticking to 1s and 2s. This may be a bit confusing when you're writing your exams, so do what suits you best, but make sure that it's in a form that the marker will understand. So firstly, we write out that the sum of the momentum before is equal to the sum of the momentum after the collision. We know that this is an explosion. Both of the objects start off in a sense as one with the same velocity. So if we plug values into the formula, we have that the mass of the bullet is 0,02, the mass of the rifle is 3, and they both start off with a velocity of 0 meters per second. After the collision, we have that the mass of the bullet is still 0,02. We're looking for its final velocity. That is what we're looking for now. And we know that for the rifle, it has a mass of 3, and in the end, its final velocity is going to be this is going to be negative. Okay, we need to, grade 12s, we need to choose a direction as negative and one as positive. Let's choose forward as positive. Okay, that means that when the rifle recoils, then its velocity is going to be negative. So into this formula, we're going to plug in negative 1,4. Okay, please don't be like me. Don't forget your direction. It is very important that you don't forget direction. So we can now manipulate the formula and plug these values into our calculators. In the end, we find that the final velocity is going to be equal to a very big 210 meters per second. This answer is positive, so that means that the final velocity of the bullet is going to equal to 210 meters per second forward. And this is the answer to this question. We're now going to look at the last type of scenario in which you may need to apply your principle of conservation of linear momentum. So this is the last problem we will deal with in this video. And it says a car of mass 1,000 kilograms traveling at 40 meters per second east collides head-on with a truck of mass 5,000 kilograms moving west at 20 meters per second. Already, to make sure that I don't forget, I'm going to choose one of these directions as positive. I'm going to go ahead and choose east as positive. This means that west is the negative direction. They now say after the collision, the car and the truck move together. Ignore the effect of friction. Question 1.1 says state the law of conservation of linear momentum. I'm going to leave that up to you. The next question says calculate the velocity of the car-truck system immediately after the collision. So we have the mass of the car, we have the initial velocity of the car, we also have the mass of the truck, and we have the initial velocity of the truck. Alright, so now we are looking for the final velocity of the system. All right, so let's go and plug in what we know into this equation. All right, so I'm using the version that we'd use when the two objects are stuck together in the end. We're going to have the mass of the car is 1,000. Its initial velocity is positive 40. The mass of the truck is 5,000. Its initial velocity is negative 20 because we are choosing towards the west to be the negative direction. Now on the right hand side of this formula, we say the mass of the car plus the mass of the truck, and we have the final velocity. So all that we now need to do is manipulate the formula and plug values into our calculators. In the end, we find that the final velocity of the system is negative 10 meters per second. But of course, we need to interpret this negative. Negative, remember, is the opposite direction to east, which is west. West is the negative direction. So that means that the final velocity is equal to 10 meters per second towards the west. In a question like this, you would probably get 1 mark for your formula, 1 mark for subbing on the left and right hand side, 1 mark for the magnitude and SI unit, and 1 mark for your final direction. This gives you a total of 5 marks. Grade 12, this brings us to the end of this video on conservation of linear momentum. In the next video, as you can actually see at the bottom left hand corner of your screen, we're going to take a look at the last section of this chapter on momentum, and that is elastic and inelastic collisions.